Well, I'm a human evolutionary geneticist, and so I'm interested in how genetics and population genetic methods and genetic data can be used to say something about human evolution. And genetics is, in many ways, a latecomer to the study of human evolution, but I think we can be fairly confident that it's made a reasonable impact in the field. And most people think, when they think about how genetics has impacted, they think about very high-profile things like Neanderthal studies and so on, ancient DNA, also looking at genetic variation in populations and saying something about, for example, competing theories like multi-regionalism out of Africa and so on. And of course, those things are important, but genetics really has contributed in two areas. So one is that genetic data and what that genetic data says about different aspects of our evolution. And there are many things which we can discuss. But there's another thing which is often ignored by the human evolutionary community, which is that genetics also has a long history of developing statistical and modeling tools. And so these are often beginning to be borrowed more and more, particularly in areas like cultural evolution, and I think in the future in many other aspects of understanding, for example, the fossil record, and trying to piece together and integrate different types of data as they used to tell us about human evolution. But I'll start with the genetic data itself, because of course that's the firm thing that we're mostly familiar with. So we can look at genetic variation in people alive today, and that carries with it some information about firstly about our demographic history, so how people have moved around, how populations are related to each other when expansions, range expansions or bottlenecks and so on have occurred, and it's made quite a substantial contribution over the last 20 or 30 years. So those kind of understandings. Then there's another area which is in many ways more interesting, or at least to some people, which is about natural selection. So our genomes also carry information about what traits have been under natural selection, or at least what genes have been under natural selection. Of course, there's always a discussion about how do genes map onto traits, and sometimes it's simple, but most of the time it's actually really quite complicated. But certainly we can identify genes that show signatures of natural selection. And there are many ways of doing that have many different temporal scales, from tens of thousands of years to tens of thousands of years up to sort of hundreds of thousands of years, up to millions of years. So those can make important contributions, I think. And we can, for example, ask questions about the evolution of the ability to digest certain nutrients, the evolution of skin coloration, and many other phenotypic characteristics. Then there's a new component, which is ancient DNA, and this really adds significantly to what we can say. It adds significantly for two particular reasons. So firstly, it gives us more of a temporal dimension to the genetics. Without ancient DNA, we are simply stuck with variation, and then we have to know what mutation rates are to know what that can say about times in the past. But with ancient DNA, it gives an extra temporal dimension. And secondly, and perhaps more importantly, ancient DNA gives us access to extinct species, extinct hominids. And that of course is extremely important, because for one reason or another, we have a number of extinct hominid relatives that are absolutely central to debates about the nature of human evolution, including, of course, things like Neanderthals. So I think, and there have been many contributions, too numerous to mention now, but you could say that genetics has essentially supported mostly a recent African origin, but we now know that the picture is likely to be more complicated than that. So, and there are, of course, many uncertainties with genetic influence. Moving on to what the body of theory in population genetics brings to other subjects? Well, many of the greatest statisticians of the last 100 years were in fact population geneticists, and they took statistical inference and the idea of, more lately with fast computers, modeling to a very advanced level, and to such an advanced level that it's now able to spill over into other areas of making inferences about human evolution that aren't necessarily to do with genetics. For example, we can now think quite legitimately about modeling processes of cultural evolution, and then being able to make direct inferences about how cultural evolution affects human evolution, what the modes and rates of change are. And this can only really be done properly using those kind of inferential frameworks that are coming out of statistical developments in population genetics. And there are a number of new ones which I think are particularly important, new developments in that field. So one is the ability to actually explicitly simulate histories or evolutionary histories. And if we can explicitly simulate them, then with those explicit simulations, we can use those to generate simulated data, and we can compare that simulated data to real data. And using that approach, we can identify the evolutionary conditions that best explain the data that we actually observed. And that could be fossil data, material culture data, and so on. And one of the great advantages of being able to explicitly simulate and histories and compare those to real, their outcomes to real data, is that we find ourselves in a more secure statistical framework. We can account for uncertainties, and we can also we can pick up on phenomena that are counterintuitive. Many people use the word emergent. So there are a number of properties or emergent phenomena that come out of, for example, expansions of populations in space that 10 years ago or so, nobody would have ever even considered. And yet now we know are important. So the ability to actually recover those emergent phenomena and take account of the uncertainties in the data and the uncertainties in the sampling, I think that's going to have in the long term, that's going to have a profound effect on how we understand and how we approach questions in human